SwayamPrabha. Digital India. Educated India.
Hello everyone, welcome back. In the last class we started the 1M1 stability analysis, and we saw that how we can use the Fourier form or the waveform of your input function and find out whether a discretization scheme is stable or not. There are certain restrictions we talked, let us say that the equation should be linear and then it should be periodic, but even with those restrictions we are able to get some useful information. Okay. So, what we did in the last class, just briefly go there. Okay. So, we use this forward in time and central and space scheme for the diffusion. So, this is our diffusion scheme. Okay. And when we use the forward in time and central and space, so this will become u I n plus 1 minus u I n by delta t will become nu, and that will be u I plus 1 n minus 2 u I n plus u I minus 1 n by delta x square, right. And you can basically modify it and rewrite it, rearrange it, and you will get this form. Take this as alpha, okay, and then use the form u is equal to z to the power n e to the power I phi, right, I n. So, remember this small I is the grid index, okay, and this n is the basically the you have the discretization time also, this is you can call it time index, okay, and this capital I is basically the square root of minus 1, right. So, you can use this form, and finally, what is our desire, what we want is basically the amplification factor g, which is given by g to the power n plus 1 by g to the power n, right. And once you do that, you rearrange and you will find our g value, amplification factor value like this, right. And then you know that the sign value cannot become greater than 1, and you basically use this the g should be between minus 1 to 1, and you will find out that this scheme, which is basically the FTCH scheme, is stable for 0 to alpha to 1 by 2, right. And this is what we have seen earlier also while trying to solve our diffusion problem using finite difference approach, right. And we saw that when the this diffusion number alpha goes greater than half, then you start seeing some wiggles and quickly it becomes unstable. So, in today's class we will look at some more discretization schemes and find out whether they are stable or not. So, the scheme can be stable, okay. So, stable also it can be unconditionally stable, okay. That means regardless of what alpha you have, or in the case of convection equation the lambda you have, it will become stable. So, this is, or it can be conditionally stable like what we saw in the case of FTCS, okay, for diffusion, right. So, we saw that alpha is stable, the scheme is stable only alpha is less than equal to half, right. And then you can have unstable schemes, okay, and that also it can be unconditional or conditional, okay. It can be, I mean, conditionally unstable is basically also conditionally stable, but you can have unconditionally unstable system. That means regardless of what alpha or lambda value you use, it will always be unstable. Okay. So, let us look at some more schemes, let us analyze them for the stability properties. So, we will stick to the diffusion equation as of now, okay. So, this is del u by del t equal to nu del to u by del x square, right. And you are using u equal to z to the power n e to the power I phi, right, and this is I, okay. So, now we are going to use implicit scheme. Okay. That means, our del to u, the right hand term that you are discretizing, that will also be at the time step n plus 1. Okay. So, this can be easily written as u I n plus 1 minus u I n by delta t. If it were explicit, you could write nu, use the central differentiation scheme, that will become u I plus 1 n minus u 2 u I n plus u I minus 1 n by delta x square. But this was what we derived discussed earlier, but since it is implicit scheme, this will also be at n plus 1, n plus 1 and n plus 1. Okay. That is the only change between the explicit scheme and implicit scheme. Okay. So, now let us start using this form. Okay. The Fourier answer is there. So, this is my u I n. So, u I n is equal to zeta to the power n e to the power I phi, okay, and then u I n plus 1 will become e to the power n plus 1 e to the power I phi, and u I plus 1 n plus 1 will become e to the power n plus 1 e to the power I plus 1 I phi, and u I minus 1 n plus 1 will become e to the power n plus 1 e to the power I minus 1 I phi, right, and use all these values here. Okay. This is a very simple analysis, you just have to rearrange terms and find out the value of zeta to the power n plus 1 by zeta to the power n, okay, mod of this may be. Okay. This is your amplification factor. Okay. For all the schemes, we need to find out the conditions at which g is less than 1, right. So, when you use all those values, what will you find? So, first rearrange it, I write u I n plus 1 will be u I n, and nu delta t by del x square I will write as alpha plus alpha u I plus 1 n plus 1 minus 2 u I n plus 1 plus u I minus 1 n plus 1, right. So, this will become zeta to the power n plus 1, and then it will become e to the power I phi, right. So, what I will do, I will take this e to the power I phi common. So, this will be e to the power I phi will be there everywhere, right. So, I will take that common outside, this will become zeta to the power n plus alpha, and then this is e to the power, this can be written as zeta to the power n plus 1 e to the power I phi, and then e to the power I phi, right. That is what it will be. So, this will be e to the power I phi minus 2 and plus e to the power minus I phi, right, like we have done earlier, and this entire thing is basically multiplied by e to the power I phi. Okay. So, this you can now, and there will be zeta to the power n plus 1 here also, right, because everything is at n plus 1, right. So, now you can just remove this, okay, and now rearrange this, zeta to the power n plus 1 will be zeta to the power n plus, now what is this? So, we have discussed about the Euler's equation, e to the power I phi is equal to cos phi plus I sin phi, and e to the power minus I phi will be cos phi minus I sin phi. Okay. So, if you sum that up, that will become 2 cos phi and there will be minus 2, right. So, this is alpha e to the power n plus 1, you can take 2 outside, okay, that will be cos phi minus 1, right. And then you can collect all of the zeta n plus 1 terms together, that will become 1 minus 2 alpha, okay, and let us write it like this, 1 plus 2 alpha 1 minus cos phi, right, will be zeta to the power n, right. And we have discussed this 1 minus cos phi will be sine square phi by 2. Yeah, this is the basic trigonometric equation, right. So, you can write this g to the power n plus 1 by g to the power n will be 1 by 1 plus 2 alpha sine square phi by 2, right. Now, you can observe this expression closely, and because you know that sin alpha value is greater than 0, okay, sin phi value is greater than 0 and less than 1, right. So, this term, because the numerator is basically smaller than the denominator, right. So, numerator is 1 and denominator is 1 plus 2 alpha sin square phi by 2. So, this will be always less than equal to 1. Okay, if phi equal to 0 or pi, then it equal to 1, otherwise it will be always less than 1, right. So, that means what do we understand from this, that this discretization scheme, the implicit scheme is for basically the diffusion equation in this case is unconditionally stable, right. There is no condition here, okay. For any value of alpha you will have the this thing stable, okay. Remember here alpha is a positive number. What is alpha? Alpha is nu delta t by del x square, right. So, if so delta t is positive, delta x is positive, if nu is positive then it is always less than equal to 1, okay. If you see nu is negative, okay, then we have to be little bit careful, because you will see that this term 1 plus 2 alpha sin square phi by 2 will become less than 1, and then zeta to by n plus 1 by zeta to by n will become greater than 1. So, then it will basically blow up, right. So, if nu is negative, okay, nu is equal to negative, then your alpha is basically less than 1, and in that particular case you will have less than 0, I mean, okay. So, this will be negative and your scheme will blow up, and that is what we have seen earlier also, that if your viscosity is negative, okay, or diffusion coefficient is negative, your scheme will blow up. So, what does it mean? That instead of dissipating, which is the nature of the diffusion scheme, what will happen, that it will start exploding, okay, and quickly the scheme will become unstable, right. So, nu being positive is an essential criteria for the diffusion equation, okay, for it to be stable. Okay. So, now we looked at the diffusion equation. Now, let us look at some of the convection equations. Okay. So, we will go to the convection equation. Okay. What is the convection equation we have been following? U del u by del t plus c del u by del x equal to 0. Okay. So, we will start with FTCS, okay, forward in time and center in space, right. So, this can be written as u I n plus 1 minus u I n by delta t, our temporal term, plus c u I plus 1 n minus u I minus 1 n by delta x equal to 0, that is the discretization of your second term, okay, the convection term. So, that can be written as u I n plus 1 will be equal to u I n minus, so there will be c delta t by del x, which I will denote by lambda. So, lambda is equal to c delta t by del x, okay, and this is u I plus 1 n minus u I minus 1 n, right. So, this is our discretization scheme which will be used, okay. Again go back to our Fourierian surge. So, you have u I n will be g to the power n and e to the power I phi, right. So, remember as we have discussed, so this should be actually sigma z to the power j n e to the power I phi j, right, j equal to minus n to n, right. So, this is basically combination of many different waves, right, but what our stability criteria says, our stability condition says is that for any of the wave between j equal to minus 1 to n, it should not grow basically unbounded in time. Okay, that is the criteria. So, we can analyze any given wave, right. So, that is why we are taking out the summation sign, and we are just working on any wave. Okay. And ui minus 1 n equal to g to the power n e to the power I minus 1 phi, and ui plus 1 n will be g to the power n plus 1, sorry, g to the power n, this is not an implicit scheme, e to the power I plus 1 phi. Okay, put all these things here, and this will become e to the power n plus 1. Again, you can take this e to the power I phi common. Okay, it will cancel out on both the sides. Okay, will be equal to g to the power n. Okay, minus lambda, and this will become e to the power I phi minus e to the power minus I phi. Okay, and there will be actually 2 delta x, this is lambda by 2, right. That is the discretization scheme because it is a central differentiating, right. Use our formulation. Okay. So, e to the power I phi is equal to cos phi plus I sin phi, and e to the power minus I phi is equal to cos phi minus I sin phi. Okay. So, now is the subtraction. So, that will become e to the power I phi minus e to the power minus I phi will become 2 I sin phi, right. So, this can be written as n, there is a multiplication of g to the power n here. So, this is g to the power n 1 minus, now this is lambda by 2 into 2 I sin phi, right. These 2 will cancel out. Okay. So, that is g to the power n equal to 1 minus I lambda sin phi. Okay. So, what is the amplification factor? Now, see, this is now a complex number, right. So, amplification factor is g equal to g to the power n plus 1 by g to the power n, which is basically 1 minus I lambda sin phi, right. So, how do you get the magnitude of this? Okay. So, you know the property of the complex number. So, g is equal to 1 minus I lambda sin phi, right. Yeah. So, you want to get this magnitude. So, that will become g star. When it is a complex number, you multiply with its other component. Okay. So, that will be 1 minus I lambda sin phi and 1 plus I lambda sin phi, and that will become 1 minus I square lambda square sin square phi, which is 1 plus lambda square sin square phi. Okay. So, what do we see? So, my g star or g square is basically 1 plus lambda square sin square phi. Now, look at this closely. Okay. Now, lambda is a positive number, lambda is c delta t by del x, right. So, c is the speed of sound, which is positive. Okay. And we have delta t, which is the time discretization, delta x which is the space discretization, and sin phi is basically between 0 to 1, right. That means, this value 1 plus lambda square sin square phi will always be greater than basically 1, right. If sin phi is equal to 0, then it will be equal to 1, otherwise it will always be greater than 1. And this is c lambda square, c does not matter if the c is positive or negative, it does not matter, lambda square is always positive. So, my FTCS for convection is what? Unconditionally unstable. Okay. So, that is why if you recall, when we tried solving this FTCS using the FTCS scheme for let us say advection of a square wave, okay, and we saw that it started developing wiggles and then quickly it basically blew up. As you run in time, it will quickly blow up. It is supposed to be convecting with the convection speed. So, in this case it is speed is equal to c. So, it is supposed to go like this, okay, but instead you will start developing wiggles like this and finally it will basically blow up, right. So, because this scheme is unconditionally unstable, right. Now, let us do this central differentiating, but with an implicit formulation. Okay. So, del u by del t plus c del u by del x equal to 0, we want it implicit with central differentiating. Okay. So, this will become u I n plus 1 minus u I n by delta t plus c u I plus 1, and this will be n plus 1, right, minus u I minus 1 and n minus 1. No, that will be n plus 1 only, I minus 1 n plus 1 by 2 delta x, right. So, because this is implicit, you have both these terms at n plus 1, right, and we are trying to analyze this scheme for stability. Okay. So, this will become u I n plus 1 equal to u I n minus lambda by 2 u I plus 1 n plus 1 minus u pi minus 1 n plus 1. Okay. Very similar to the explicit scheme, except that we have this n plus 1 term instead of n term. Okay. So, put the Fourier and such. Okay. This may become zeta by n plus 1. I am taking the e to the power I phi I phi s outside. Okay. So, this will become zeta to the power n minus lambda by 2, and then this will be zeta to the power n plus 1, right, because this is all at n plus 1. Okay. I basically request you to go back and derive it all for yourself, because I am going little bit fast, but it is not very difficult. You just have to rearrange terms, do the algebra little bit carefully, and you should be able to do it. Okay. So, then n plus 1 term I have already taken, this will become the power I phi minus e to the power minus I phi, okay, and this we have already seen, okay, that value is 2 I sin phi. Okay. So, this is zeta to the power n plus 1 into zeta to the power n minus d to the power n plus 1, and this is lambda I sin phi, because 2 and 2 will cancel out, right. This will become 1 plus lambda I sin phi zeta to the power n plus 1 will be equal to zeta to the power n, right. So, the amplification factor g will be zeta to the power n plus 1 by zeta to the power n, that will be 1 by 1 plus lambda I sin phi, right. So, now we have to find out whether this scheme is stable or unstable, right. So, now again it is a complex number, right. So, what we will do, we will write it in a proper complex number form. Okay. We will rearrange the terms, that will be 1 plus lambda I sin phi. Okay. We want to see whether it is less than 1 or greater than 1, right. So, that will become 1 minus lambda I sin phi by 1 plus lambda I sin phi, right. Or I think before that, what we can do, we can multiply top and bottom with 1 minus lambda I sin phi, that will be better. Okay, we can work it either way. So, that will become 1 minus lambda I sin phi, and this is 1 plus lambda I sin phi, 1 minus lambda I sin phi. So, that will become 1 minus lambda I sin phi by 1 plus lambda square sin square phi, right, this term. We have done that already, okay. And so, this is 1 plus lambda square sin square phi minus I lambda sin phi by 1 plus lambda square sin square phi. Okay. So, do G star. Okay. So, in the G star it will be the conjugate. So, that will become this I and the minus will become plus. Okay. So, ultimately what we will have is on the top we will have 1 plus lambda square sin square phi, okay, when you do G star, and bottom will be, it will be multiplying 2 times, right. So, that will be 1 plus lambda square sin square phi whole square. So, then this will get cancelled out, and what we will have is 1 plus lambda square sin square phi, right. So, you can see this that sin phi is between 0 to 1, okay, and lambda is greater than 1, lambda square of course is greater than 1. So, then this G star is basically less than 1, right, or more accurately less than equal to 1. So, even if we use the central differentiation scheme for the convection equation, we find out that the scheme is stable, unconditionally stable. Okay. So, this is a very good observation that when you use the explicit scheme with the central differentiation, the scheme is basically unconditionally unstable, but when you just change it from explicit to implicit, you find that scheme is unconditionally stable. So, the implicit schemes by default are unconditionally stable for any flow. Okay. Of course, this analysis is limited to the linear flows. Okay. So, whether you have the convection or the diffusion, linear convection, linear diffusion, you will see that you can apply the implicit scheme, and that will always give you the stable solution. Okay. Now, one thing is remaining that needs to be seen, as we have discussed earlier. For solving this FTCS scheme, solving the convection problem, we have used this FTBS scheme, right, FTBS, and we have found and we have seen it many times that the scheme is stable for lambda less than equal to 1, okay, or basically C delta T by del x is less than equal to 1, right. This we looked at through our practical experience when we tried solving the problem, the convection problem. Also, we have seen it from the modified PDE, okay, where we saw that the diffusion term, the modified PDE actually consists of a diffusion term, and that becomes positive only when the C delta x less than equal to 1, and that is why we are able to solve it. We will in the next class what we will do, we will use the von Neumann stability analysis, okay, the way we are doing, and we will see if we are getting the same thing for the FTBS scheme. Okay. So, with that we will stop for the class today, and we will meet in the next class. Thank you very much.